Hey Explorers, welcome back to another episode of Virtual MOSI. My name's Catherine, and today what we have for you is an engineering challenge. It's all about bridges today. So you saw a couple different examples here that I built earlier from toothpicks, and you're going to get a chance to do those later in this video. So you see I have three kind of examples here, right? I have what's traditionally known as a truss bridge, an arch bridge, and a suspension bridge. And I want you to take a look at these. What kind of shapes do you notice within them? Maybe some squares, some triangles, some trapezoids, a bunch of different shapes, right? And some shapes are in fact stronger than others. So I have some examples here. Here's a little triangle, a little square, and a little trapezoid, kind of like a squished square. So which ones do we think are going to be stronger? I'm going to try to push down on some of these and see if we can get them to break. Are you ready? We'll start with the trapezoid. Ooh, that didn't take much at all. Just one finger. We'll try the square. Quite a bit stronger. I'm pushing with a lot of force now. Maybe if I put two. Okay, finally. And then if I have the triangle, I can push as hard as I want, and it's not really breaking. I'd have to get something really big to bust this. So we have kind of stronger shapes and weaker shapes, right? Why are some shapes stronger than others, though? Well, it all has to do with how they distribute force. And scientists measure force, the direction of it, I should say, using something called vectors. It's really easy. It's just an arrow representing the direction of the force. If I draw an arrow like this, I'm telling you that I have a force going that way. And if I draw it really big or really long, that means it's a much bigger force. So when I have my square, we might have forces like this. I was pushing down, so it's going on this beam here and this beam here. And then when I had my triangle, that force that I was pushing wasn't just going down, it was also going to the sides. So it's kind of split up a little bit more, which helps make it stronger. And there's two main forces I want to mention that are going on in our bridge. And as soon as I explain them, we're going to go back and see if you can detect them. So we have compression. Compression is when you have two forces pushing against each other, like this. Kind of like if you're carrying something heavy and it's weighing down your spine, you're being compressed. So, compression. The two forces are pushing against each other, and that can break your bridge. And then we also have tension. Tension is the exact opposite. It's when those forces are going in opposite directions, trying to pull something apart, like snapping a rope. So we might have one going up and one going down. And there are more forces, of course, at work too. But these are the major ones I want to talk about today. So let's look over at our bridges real quick. Where do you think some of the force is going? If you were going to draw arrows on these bridges, which direction would the forces be going? Well, I think on the arch we would have some going down here. We would have some going down here, right? If I put a weight on top. And arches are very, very strong bridges. They kind of are, this curved shape helps us distribute that force much better than something that was just flat. This is going to break a lot easier, this truss bridge, than our arch bridge. And that's why a lot of really old bridges made of stone have lasted, because they were made with that nice shape. Truss bridges, though, are really simple. They might not be as strong, but they're really quick to build. And they don't take a lot of forethought, a lot of effort, and you don't need as much materials, you don't need as much skill to build them, so they're really convenient if you need something kind of quickly, or you don't have a task that's going to be very, very heavy. Now, suspension bridges are really interesting. And the suspension bridges have forces that are going down, okay, but also going out. Especially take a look at these ropes here. They're pulling up, but also at an angle. So we have an upward and a horizontal component to our vector here. And that's helping support the bridge using only these very, very, very skinny towers. That's the benefit of suspension bridges, is they can span long, long distances with relatively few materials. So you don't necessarily need all of the individual toothpicks that you would need to build a big arch like this. You'd need a lot of stuff versus just some thin, skinny ropes to help you distribute that force. And it's actually even stronger when you can anchor the ends of it down to either side of your span that you're trying to cross. Okay, so I'm going to build a bridge with you. And as we do, I'm going to tell you a little bit more about suspension bridges. So, okay, if you want to build a bridge at home, you're going to need a couple things. Toothpicks or popsicle sticks or skewers, something like that. I've got a hot glue gun. That works very, very nicely. You could also use tape. And a good way to start is to design your bridge. So think about what kind of bridge you want to build. What kind of shape is it going to have? What's the purpose of your bridge? Do you have a lot of toothpicks you can use? Or do you only have a few? All of these are engineering considerations that you're going to have to make. So I am going to draw out a little bridge for myself here on my paper, because that's going to be helpful in making sure that both sides are the same length. Okay, so 4 toothpicks. So I'm going to want one here, one here, one here. And you can either lay them out first or sketch it out first, whatever is easier for you. And then I'm going to want some triangles, because I know triangles are a nice, strong shape. Okay, very nice. So what kind of bridge am I building here? It's a truss bridge, right? And I'm choosing to design a truss bridge because, like I said, they're quick and easy to make. But you at home, feel free to design any kind of bridge you like. Try different shapes. Okay, cool. I'll get that, I'll get that. Awesome. So you can just put a little hot glue every place you have a connection. And I'm just going to hold them all there for a second until they dry. If you do this on paper, it's going to rip up a little bit. That's fine, so I don't mind. But if you don't want that, go ahead and do it on some plastic or some metal, something that glue is not going to stick to. Definitely don't do it on like a rug or something like that. All right. And yeah. So truss bridges don't span typically very far. If they did, the longer they get, the kind of weaker they get in the middle, which is why a lot of really long bridges around the country use suspension bridges, and it was a very innovative technology when they were first invented. The Brooklyn Bridge is an excellent example of a suspension bridge. It was the longest suspension bridge in the world at the time that it was built. And it spans Brooklyn and Manhattan, which were previously 2 separate cities before they had a way to be connected together by one bridge. It's kind of an interesting story how it got built. It was designed by an engineer of the last name Roebling. So he actually designed the bridge, but then before he could actually build the bridge, he passed away. And so his son, Washington Roebling, took over. And he finished up some of the construction plans and started building the bridge a little bit. But not more than a couple weeks into the project, he ended up getting terribly injured in an accident and could not continue building the bridge. He had to actually stay home and recover for the entirety of the project. So who took over? Well, luckily, he was married to another engineer. His wife, Emily Roebling, actually took over the project for him, and she was the one who actually saw the Brooklyn Bridge built. So she oversaw the designs and oversaw the building of it and all the supplies and everything that was needed to build it for this massive project that was really one of a kind at the time. and kind of prove to the world that these types of bridges, these designs of bridges, could work in a large setting, like on a large scale. And of course, now we have other famous suspension bridges around the world, and particularly in the United States, including the Golden Gate Bridge in San Francisco, anywhere you have to span these large, long distances. So, kind of cool. So when you build your own bridge like this, it takes a while, so you got to be patient. And after you finish building one side, you're going to copy it. So you're going to build the exact same thing again, and those will be the two sides of your bridge. Now, you can try to do the project alone, like Washington Roebling did, but if you work together with a partner, like when the two of them work together, Emily and Washington, your bridge is going to come together a lot faster and a lot nicer. So I highly recommend you try this engineering challenge with a friend, if you've got one, or a sibling. Somebody who wants to build a bridge with you. And it's really fun if you want to test them out and see if they can break, how much weight they can support, things like that. Okay, so this is going to be a really, really, really tiny bridge. Okay. I think you kind of get the idea there. Oh, that's kind of stuck to the paper. That's okay. Okay. So if you were building your own bridge, you'd build it like this. You'd check and see if there's any weak spots. Add a little more glue. Copy that, and do it again. Now, if you want to build a suspension bridge, I just used regular string. You can use anything you want. I just looped it over the end here, and I tied it to every individual truss or support beam along the way. And if you want to make it extra strong, you can actually connect them from both sides to every single truss. I just had them meet halfway. So, I thought a fun thing we could try to do is try to put a little weight on top of these bridges and see if they can support it. So let's see. We'll start with our truss bridge. Let me see, I think I had a book somewhere. I'll go grab a book, hang on. All right. Let's see if it can hold at least one book. It's a little wobbly, but it's lasting. It's pretty good. Put another one. Woo! Not very stable. Oh man, can you guys see that wiggle? It's not going to last very well. Okay. Let's see if we get the same amount of wiggle with my arch bridge. We'll start with one book. Not too bad. Not too shabby. Put another one. Woo-hoo-hoo. Now it's wobbling a little bit. And I'll have to anchor both sides. So this is another thing that engineers have to consider is natural disasters, like earthquakes or hurricanes, things like that. So when you build your bridge, definitely test it out and see how much weight you can make it hold. And don't forget about vectors. Think about the direction of your forces. Think about how you're distributing that weight. Is there going to be any tension? Is there going to be any compression? And hopefully you can build a bridge that'll last. Thanks for joining us today. I hope you guys try this engineering challenge. If you do, definitely drop us some pictures in the comments. We'd love to see them. And as always, keep discovering.